Alright, hello everyone. I hope you guys are doing good and keeping safe. So today I will be discussing the solutions to Atcoder Beginner Contest 234. This contest has just ended, and talking about the contest, I think this was a pretty typical ABC. I would say it was a bit easier than a normal ABC. In fact, the first 4 problems were really easy, and even the 5th problem this time was not that hard as compared to previous ABC rounds. And Problem F was real good. Problem F was amazing. So yeah, all in all, a good contest, and I would say a little bit easier than a general ABC round, right? So today I will be discussing the first 6 problems from A to F. The first few problems were just really easy, so I will be discussing them just like that in a breeze, and I'll be talking in detail about the last 1 or 2 problems. So yeah, let's get right into it and start with problem A. Okay, so in this problem we have a function f where f of x is x squared plus 2x plus 3. So given an integer t, we need to find this expression, and we have been assured that the answer will never exceed 2 into 10 raised power 9. So that means we don't have anything to worry about, and basically we can just write a function which returns x squared plus 2x plus 3 and takes in x as input, and just copy paste this expression that they have written, and that would just blindly give us the answer, right? So we don't really have to do anything much in this problem, so I don't think we have much to discuss here. Let's just have a quick look at the code. So just write a function which takes in x and gives x squared plus 2x plus 3 as output, and read into the input n and just output the function which they have provided you in the problem, right? So you can just copy paste it and that will just work, right? So yeah, this completes problem A. Nothing much to talk about here. So let's move to the next problem, problem B now. Okay, so in this problem we have been provided with n points in a 2-dimensional plane, and the coordinates of the ith point are xi comma yi. Basically we need to find out the length of the segment connecting these 2 points such that the length is maximum. So we need to find the maximum distance between any 2 points basically, right? The key thing to notice here is that n is only up to 100, and so a brute force will just work here. All the xi and yi values are also really small. So if n was up to 10 to the 5, then this problem becomes really difficult and some advanced algorithms are needed to solve this. But since here the value of n is small, we can just do a brute force and calculate the distance between each points. So that would be O of n square. We will iterate on each pair of points, and the number of points are O of n square. The number of pairs of points are O of n square, and the distance between any 2 points xi yi and xj yj is just under root of xi minus xj square plus yi minus yj square. That's just basic high school coordinate geometry. So yeah, we can calculate the distance in O of 1, and we can iterate over all pairs, so the time complexity becomes O of n square, which is good enough to pass the time limit here. So that's what we are going to do in this problem. Let's just have a quick look at the code. Right, so first of all you write this line so that all the double numbers are outputted with a precision of 10, and then you take in a final distance 0 which you need to maximize, and then read into all these xi and yi values. Then you can just iterate on each pair and find out the distance between these 2 points using square root of xi minus xj square plus yi minus yj square, right? And then the distance will be maximum of distance and the current distance, and that's it. You can finally output distance and you will get the correct answer. So yeah, this completes the solution to problem B as well. Moving on, let's talk about the third problem now. So this is a real tricky problem, and this is kind of a troll problem. So let's see what this has to say. So among the positive integers that consist of zeros and twos when written in base 10, find the kth smallest integer, right? So essentially we have all the numbers, but we can only use those numbers which contain the digits 0 and 2 and nothing else, and we need to figure out what is the kth smallest integer out of all these integers. The key thing to notice again here is that k is an integer between 1 to 10 raised power 80, and the question that I want to ask here is that does it make any difference if I use ones in place of twos, right? 1 is still greater than 0, so I am allowed to use ones instead of twos, and I will find the answer, and in the answer I will just replace all the ones by twos, and no one is stopping me from doing that because I need to find the kth smallest integer. It doesn't matter if I am using twos or ones. So basically I can just replace all these 2's by 1's, find the kth smallest integer, and then again replace all the 1's by 2's, right? And that will be correct because I'm just replacing 1's by 2's. Every 1 still remains greater than a 0. So it doesn't matter if I use 1's or 2's. So yeah, that's the first thing we are going to do. Replace every 2 by 1. But then what we notice is that if we are using only 0's and 1's, it becomes a binary number, right? It becomes a number in base 2, and if we need to find out its value in base 10, but we need to find out the kth smallest integer in base 10, but we can still treat it as a base 2 integer because basically what we are interested in is the relative positions between the numbers. So it doesn't matter if we consider them in base 2 or base 10, right? The relative position still stays the same. So yeah, this basically sums up the problem. I can replace all the 2's with 1's, and I can replace base 10 with base 2, because at the end of the day I am interested in the relative positioning of the numbers, and I need to find the kth smallest number. So it doesn't matter if I talk in base 10 or base 2. And so the problem now boils down to, I have a set of binary number system. I need to find the kth smallest integer in the binary number system, and that is nothing but the binary representation of k, right? So yeah, that's why I was saying this is a troll problem. You can just find out the binary representation of k and then replace every 1 there by 2, and that would be it. That would give you the correct answer. So as we can see in the sample, the binary representation of 3 is 1 1, so we can replace 1 1 by 2 2. Similarly, the binary representation of 11 is 1 0 1 1, and then again you can replace all the 1's by 2's and you can get the correct answer. Another thing that is mentioned here is that you don't have to output the trailing zeros. So that can be avoided using a very simple trick which I will show you in the code. So let's jump at the code now. The code again is really simple. Basically you can just figure out the length of the number by this single line, 64 minus built-in CLZ of k. So built-in CLZ is just a function which finds out the total number of leading zeros in the binary representations, and if we subtract them from 64, then we just get the length, because a long integer has like 64 bits. So if we subtract from 64 the number of leading zeros, we will get the exact length of the number, and then we can iterate from d minus 1 to 0 and check if the particular bit is set or not. If the bit is set, then we add 2 to our answer, because at the end of the day we will replace every 1 by 2. Otherwise we'll just add a 0 to our answer. So yeah, this basically completes the solution to problem C. And now let's move on to problem D. Alright, so given a permutation P of 1 to n and a positive integer k, for each I from k to n, we need to figure out the kth greatest value among the first I terms of P. So that's the problem. So for each I going from k to n, we need to figure out the kth greatest value among the first I terms of P. Now I know there can be other simpler ways to do it. Other ways to do it which are a bit implementation heavy. But the good thing here is that if you have strong knowledge of data structures, you can just throw them at problems and you can get the solution. So that is the advantage of knowing data structures. You don't have to do the laborious work yourself. Like I'm sure that they didn't intend this problem to be solved by an ordered set, but it turns out that an ordered set makes this problem really easy. So yeah, that's one advantage of knowing data structures really well. You can just throw them at problems. And so that's what you can do here. You can just maintain an ordered set and just go from k to n and use your ordered set to find the kth greatest element, right? And you don't have to think about anything else. I'm sure there might be other ways to do this problem, but the best way to tackle this problem during a contest is to just simply use an ordered set. And that is exactly what I did. So you can just maintain an ordered set of all the numbers which are in the prefix I if you are at I, and just query on that ordered set for the kth greatest element. That's a O of log n operation, and you can do that for all I from k to n. So that makes the solution O of n log n, which is enough to pass the time limit because n is still up to 5 into 10 raised power 5, right? So yeah, that is the solution. Let's just have a look at the code. So you are keeping an ordered set. An ordered set is a very special data structure which is present in the C++ GNU PBDS library. So if you want to learn more about ordered set, I'm sure there are a lot of free resources to learn from the internet, Codeforces blogs and YouTube videos. So you can go ahead and do that. But if you already know ordered set, the solution becomes really easy. So first of all, we insert all the elements from 1 to k minus 1 in our ordered set, and then we go from k to n. we insert the ith element, so that makes the ordered set contain all the elements in the prefix from 1 to I, and you just find out the element which is the I minus kth smallest element. So if it is the I minus kth smallest element, it becomes the kth greatest element, because the total number of elements in the set is just I, right? And so that's what just we want. And yeah, so this completes the solution to problem D. Really easy if you know ordered set, right? So that's one advantage of learning data structures, and ordered set particularly is a very, very useful data structure. It can be used to solve problems which are of very high difficulty and which the problem setters didn't actually intend to be solved by an ordered set, right? So sometimes there are problems of ratings up to 2300, 2400 on Codeforces, which become really easy if you just simply use an ordered set. So that's why learning an ordered set is definitely going to help you. So yeah, with that in mind, let's move to problem E. Again, I would like to say that this problem was a bit easier than a typical Atcoder beginner contest problem E, which are generally real hard. So yeah, let's see what this problem is saying. So let's call a positive integer n that satisfies the following conditions as an arithmetic number. So let di be the ith digit of n from the top, where n is written in base 10 without n necessarily leading zeros. Then d2 minus d1 is equal to d3 minus d2, and so on up till dk minus dk minus 1, where k are the number of digits in n. So this condition can be rephrased into the sequence d1, d2 up till dk being in an arithmetic progression, right? So also, any one digit number is assumed to be an arithmetic number. So basically, a number is an arithmetic number if all of its digits are in AP, are in arithmetic progression, right? So that's it. And basically, in this problem, we have been provided with the number x, and we need to find the first arithmetic number which is greater than or equals to x, right? So yeah, find the smallest arithmetic number not less than x, and if a number is not less than x, it is by order it is greater than or equals to x, right? So out of all the arithmetic numbers, we need to find the first number which is greater than or equals to x. Again, the key thing to notice here is the constraints. X is an integer which goes from 1 to 10 raised to power 17. So yeah, that's the problem. And let's try to make a very crucial observation here, which will essentially just solve our problem. So let's make a key observation here. So the key observation in this problem is that the total number of arithmetic numbers is really small. The total number of arithmetic numbers is really small. Well, really small is just a way of saying, but we need to be exact, right? We need to be sure that if we generate all the numbers, we won't TLE. So basically, we need to have some kind of an upper bound on the total number of arithmetic numbers which can exist. So let's try to prove it. So let's try to prove that the total number of arithmetic numbers are so small that we can actually generate all of them. So the condition that we want is that all digits should be in AP. Okay, so for a number to be in AP, there are a few conditions which the number should satisfy. The first condition is general for any number. The first digit, that is the leftmost digit, should be from 0 to 9, right? Like it should be from 1 to 9 basically, because so the leftmost digit, because obviously the leading digit cannot be 0, should be from 1 to 9, right? So this is a condition which every number has to satisfy, obviously. And so that's the first condition. Now the second condition is that any AP has a common difference, right? And a common difference basically means that every element in this AP, every continuous elements, every two contiguous elements in the AP differ by the same value d, which is the common difference of an AP, right? So that's just a definition of common difference. But the condition that a number should satisfy so that all of its digits are in AP is that the common difference, the absolute value of the common difference does not exceed 8 or maybe 9. Like we can just say 9, but I think it will be 8 because the first digit can never be 0. But if we just allow the first digit to be equal to 0, then the absolute value of the common difference does not exceed -9. So if we denote common difference by CD, then the common difference goes from -9 to 9, right? And the reason for that is simple, because if the common difference exceeds 9, then no matter what the first digit is, the second digit will become greater than 9, and a digit can never become greater than 9, right? All the digits have to be from 0 to 9 itself. So the absolute value of the common difference can never exceed 9. That's one thing. Also, the length of the number cannot exceed 18, and that's what comes in from the constraints. According to the constraints, x is up to 10 raised to power 17, and 10 raised to power 17 has exactly 18 digits, and so the length of our AP can never exceed 18, right? So if we want some kind of an upper bound, the upper bound can be obtained by this. So from the first condition we have like 10 values, so 10, and from the second condition we have around 21 values, so that's around 19 values, from -9 to 9, and from the third condition we have 18 values, right? So that leads to a number 3420, and this is just a very rough upper bound. The actual number of sequences are in fact also smaller than this. So in a way we have proved that the total number of APs would be around 3420, and what that means is that we can successfully generate all of them. So yeah, the key idea behind this problem is to actually generate all the APs, all the numbers which are in AP. And then once we have all the numbers which are in AP, what we can do is we need to basically find the first number which is greater than or equals to x. So the way to do that is really simple. We can just sort all the arithmetic numbers that we have generated and just use binary search to find out the first number which is greater than or equals to x. So this can be done very easily using C++ lower bound function, right? So that's the easy part, but the tricky part is to actually generate all the numbers, and that will become clear when I talk more about it in the code. So this is the code, and first of all, let me just show you the actual number of good numbers, the actual number of arithmetic numbers. So if we output the size of the vector in which I am storing all the arithmetic numbers, you will realize the actual amount of numbers is really small. It is just 524, as you can see. So yeah, the number 3000 that we came up with is just a very, very rough upper bound, but it works for us to prove that we can actually generate all of them. So yeah, now let's see what's going on. So any AP should have a common difference, right? So first of all, we will iterate on the common difference. We will basically iterate on the absolute value of the common difference, which can go from 0 to 9, right? And then any AP has a starting digit, right? So the starting digit will go from 0 to 9 again. And obviously if the common difference is 0 and the starting difference is also 0, then the number essentially becomes 0, which is not allowed. So we will just continue then. And then every AP has a length, right? And the length can never exceed 18. And so I am iterating from 1 to 18. And if I have a starting digit, a length, and a common difference, then I know the last digit also. And the last digit will just be starting digit plus length minus 1 into the common difference. So if that is greater than 9, then obviously I cannot have a valid number, because at least one of its digits is becoming greater than 9, and so I break out. And now if I have not broken out of the loop, then that means that I have a very valid combination of starting digit, common difference, and length. And so then I iterate from 1 to length, and my current number is just going to be starting digit plus I minus 1 into the common difference. And that is going to be my current digit, and I add it to my string, which is storing the current number which I am forming, right? And then I convert this string into a number using the C++ stall function. It basically takes in a string as an input and converts it into a long. And if the number is 0, then I continue. This is just a check that I'm not forming any zeros. And so I push back num into my vector of arithmetic numbers. But one thing which I'm missing out is that I only iterated for the absolute value of the common difference, not the common difference itself. So every number can be reversed, and if I will reverse that number, I will get an arithmetic number which has a common difference of minus 1 into CD. And so I will reverse the string, I will form the number again by calling the stall function, and I will push it back into my vector. So finally, at the end of the day, I will be left with all the unique values of good numbers, I mean arithmetic numbers, and all of them will be stored in the vector. So I can just sort the vector, and I can apply the C++ lower bound function here and get done with it. So yeah, this completes the solution to problem E. And now it's time to move to the last problem that we'll be discussing, problem F. And this was a really good problem. Like, I really enjoyed solving this problem. It took me around half an hour to come up with a solution, but when I was able to solve this problem, it felt really good. And so, if you were not able to solve this during the contest, I will definitely recommend you to try it out. Okay. So given a string S, how many different strings can be obtained as a permutation of a non-empty, not necessarily contiguous subsequence of S? So we have to output our answer modulo this number. So yeah, this is the problem statement, just a simple one-line problem statement, but actually it's not that easy. So yeah, the problem statement is clear enough. Let's try to solve it by making some observations. So the problem is simple. We need to find the total number of distinct strings which can be formed by permuting any subsequence of S. Right, so we have been provided with a string S. We need to figure out the total number of distinct strings which can be formed by permuting any subsequence of S. So we can take any subsequence of S and swap the values and reorder them in any way that we want. And basically then we need to find out the total number of distinct strings which we can get. Another thing to notice here is again the constraints. The constraints say that the length of the string is up to 10 to the 5. Up to 5 into 10 raised power 3, right? And a hint which is always there when the length on the constraints are up to 5000 is that O of n square works for n is equals to 5000. So they are probably trying to hint us towards an O of n square solution. That's the first thing. And also in problems like this, it is pretty much always the case that we have to use some kind of combinatorics or some kind of dynamic programming. It turns out in this problem we have to use both of them. And these kind of problems are really beautiful to me. But anyways, let's see. So yeah, that is it. So the first observation here is that since we are allowed to permute the subsequence, like since we are allowed to reorder the subsequence in any way that we want, the order in which the string has been provided to us does not matter, right? So the order does not matter. Like the order in which the characters in the string have been provided to us, they are basically just useless. So whenever you find a problem in which the order does not matter, it doesn't matter whether you come up with a solution or not. The first thing you should always do is to sort the data. So we can sort the string. Always in a problem, if you have proved that the order of the input does not matter, then try to sort the input blindly first of all, because that can never lead to anything harmful. That will always just help you. So yeah, the first thing we do is that we can sort the string. So from now on, I will consider that my string is already sorted. And now let's come to the solution. So the solution is actually dynamic programming. In problems like this, it's most of the times simple DP, simple combinatorics, or a combination of DP plus combinatorics. It turns out this time it was one of the problems which were based on a combination of DP plus combinatorics. So yeah, the solution is dynamic programming, and let's start by defining a state of the DP. So DP of ij. So I define DP of ij as the number of distinct strings of length j which can be formed by the prefix 1 to I of the sorted string. I can just omit the word sorted because I am already assuming that I have sorted the string. So yeah, this is what DP of ij is representing. It is the number of distinct strings of length j which can be formed by the prefix of length I of the string. And so it's not very hard to see that the final answer is going to be the sum of the final answer is going to be dp n1 plus dp n2 up till dp nn, right? So I need to find the total number of strings which can be of length 1, 2, 3 or up to n. And so the final answer is just going to be dp n1 plus dp n2 up till dp nn. So yeah, this is the final answer, but the tricky part is to actually look at how we are making transitions, or whether it is possible to make transitions or not. And for that, again, we need to make a few very crucial observations. So let's see. So we have a string and we have already sorted it. So there will be some A's and some B's, some C's, right? And let's say there are numbers like this, and then there are some X's, then some Y's and some Z's, right? The number of these A, B's or C's can be 0 as well. So the string will look something like this, right? That's for sure. So this is going to be my string. And let's say I am at a particular value of j and I am at a particular value of I such that s of I is z. So this is my I. And this is my I, and I need to find dp of ij for any arbitrary value of j. But the I is lying on a the I is at that index such that s of I is equal to j. And now I need to make transitions from dpij. So what is dpij equals to? It is equal to the number of distinct strings of length j which can be formed by the prefix of length I. So obviously, if I am forming a string of length j from a prefix of length I minus 1, then that has to be included in dp of I. So first of all, dp of ij is dp of I minus 1j. Now I have already included all the strings which are being formed from the prefix of length I minus 1 and which have a length of j. Now the other things which are left is that the strings which are formed from the prefix 1 to I and necessarily contain s of I and of length j, right? Because if a string does not contain the ith character, then it just becomes a string which is formed by the prefix of length I minus 1, which is already included in dp of I minus 1j, right? So yeah, that's one thing. So now we have reduced the problem to dp of ij is equals to dp of I minus 1j plus the number of strings which are formed from the prefix of length 1 to I, and they necessarily contain s of I and of length j, right? Okay, now let's move forward. So this is my I and I have a few z's before my I. So let's say the total number of z's here are count before i's. So let's say that the total number of z's here are count. So I have count number of z's and then I have some y's, some x's and so on, right? Okay, so I made a claim. I will make a claim. The claim is that so let's say that these extra strings are x. So a string will contribute to x if and only if it contains count number of z's. That is my claim. So the string will contribute to x, which is the number of strings which necessarily contain s of I and they are of length j. A string will contribute to x if and only if it contains count number of z's. And the proof again is really simple. If I don't use count number of z's, I am left with count minus 1 number of z's. And if I'm using count minus 1 number of z's, then I'm basically making a string from the prefix of length I minus 1 only, right? Because in the prefix of length I minus 1, I have count minus 1 amount of z's available to me. And so if I'm using a number of z's which are between 1 to count minus 1, then I'm basically not using the prefix I at all. I'm just using the prefix I minus 1, and that particular string will be included in dp of I minus j itself. So the proof is that if I use less than count number of z's, then any string which will be formed will be included in dp of I minus 1j, right? So yeah, if I don't use all the z's available to me, then that means I have already counted that string and that will lead to overcounting. So I need to avoid overcounting, and the way to do that is to use exactly count number of z's. Okay. So if I use exactly count number of z's, then basically what is happening is that I am using some characters in this prefix, that is from a to y, and I'm taking some characters out of them, using those characters, permuting them, and then after that I am adding count amount of z's at arbitrary locations in these permutations, right? Okay, so what happens is that we will take a string which is formed from the prefix. So this prefix is nothing but I minus count, right? So this prefix is nothing but I minus count. This is I and I have count amount of z. So this prefix is just I minus count. So we will take a string which is formed from the prefix 1 to I minus x. And so we will take a string of length j minus count. This is also important because the final string that I want should be of length j, and if I am taking count number of z's, then the number of remaining characters becomes j minus count. So I will take a string from the prefix of length 1 to I minus x of length j minus count and add z's and add count z's at arbitrary locations. Right? So basically what happens is that I am taking a string of length j minus count which can be formed from the prefix of length 1 to I minus x, and the number of those strings are basically just dp of I minus x j minus count. And so yeah, for any string which can be formed from the prefix I minus x and of length j minus count, I'm just taking that string and adding count amount of z's at arbitrary locations, right? So let's fix s as the string of length j minus count taken from the prefix 1 to I minus count. So I am fixing the string s, and so let's say I have s. So s is equals to something like this: s1, s2 up till s of j minus count. So this is s and it has already been fixed. So if I'm fixing the string, that just means that I can fix s and I can figure out the total number of strings that I can generate from s, and then I can just multiply my answer by dp of I minus x j minus count, because the number of s's that I have is dp of I minus x j minus count. So basically I can fix s and then figure out the total number of strings that are being generated. So I have j locations, right? I need to form a string which is of length j. So I have j locations, right? Let's say these are the j locations that I have. So since I have fixed the string s, what I can do is that I can choose any arbitrary count locations from these j locations and place my z's in those count locations. And once I have placed all the z's, there is only one way to place these remaining j minus count characters, which is in this order: s1, s2 up till s of j minus count, right? So basically we can choose count places out of these j places and then place all the z's in those count places. And so the remaining places will be filled by the characters of s in the order s1, s2 up till s of j minus count, right? So there is only one way to fill the remaining places, and that is in the order from s1, s2 up till s of j minus count, right? And so the only permutation here that's happening is that we are choosing count places out of the j places, and the number of ways to do that is c of j comma count, right? So we are choosing count places from the j places. And so also remember that we were fixing the string s and the total number of string s's. So the number of s's that we have is dp of I minus count j minus count. And so the transitions are now simplified, and we have completed the transitions as dp of ij is equals to dp of I minus 1j plus dp of I minus count and j minus count multiplied by c of j comma count, right? So yeah, this completes the solution, where count is the total number of consecutive z's that I have before the index I. And now this is just for an arbitrary value. I have taken z, but this basically applies to every position I, right? So count is basically the number of characters which are equal to s of I to the left of I. That's basically what count is. So yeah, this basically completes the transitions to dp, and that's it. That's the entire solution. This is a bit tricky and difficult to come up with, but it's really good if you want to practice dynamic programming. So that's it. Let's have a look at the code now. Okay, the code is small. First of all, you generate this NCR stuff. This is really easy. If you don't know how to write the code to find out NCR, then again, there are various resources you will find, and you should really learn about it. And yeah, so you take the string. You first of all, I have converted my string into a vector of numbers from 1 to 26. That's just the way I like it. And then I'm sorting my vector, and then I create a DP array, DP n comma n, where DP ij stores the number of strings of length j from the prefix of length I. The base case is simple. If j is equals to 0, that is, if the length of the string is 0, then it doesn't matter which prefix I am at. DP of I0 is just going to be 1, which is the empty string, right? So it's just going to be one string. Then I iterate for j from 1 to n, and I also iterate for count from 1 to n. I initialize count by 0. I'm just maintaining this count. It's not easy to see how we can maintain count. So if a of I is not equals to a of I minus 1, then I'm doing count equals to 0. And otherwise I'm just incrementing count, right? And the other number of the other characters will be j minus count, right? So first of all, dp ij will be dp of I minus 1j. Also, if others is 0, like if others is less than 0, then it doesn't make any sense because j minus count is becoming less than 0, so that doesn't really make any sense. We can just continue. Otherwise, we will figure out what we have to add. First of all, the thing which we have to add is simple: dp of I minus count and j minus count multiplied by c of j comma count. J comma count and j comma j minus count are just the same things, so I can also write count here, and I can replace this others by j minus count as well. That really doesn't affect anything. So yeah, dp of I will be dp of I minus 1j plus dp of plus add, where add is dp of I minus count j minus count multiplied by c of j comma count. So yeah, dp ij becomes dp I minus 1j plus dp of I minus count j minus count multiplied by c of j comma count. And by doing that, every time to the answer I am adding dp of n comma j, and finally I will have the correct answer with me. So yeah, this basically completes the solution to problem F, and that is it for today. That is all the problems that I had in mind. So thank you so much for watching, and I will see you in the next one.